Next paper, Luiz Gustavo Reis Bernardino from São Paulo State University, here, Brazil, with the paper Deep HarDec, Deep Neural Network Applied to Estimate Harmonic Decomposition. Luiz?
Good afternoon. To this afternoon, I will present the paper Deep HarDec, Deep Neural Network Applied to Estimate Harmonic Decomposition. The introduction of this paper is the increasing presence of non-linear loads in electrical system that is leading to the circulation of harmonic currents that are known for causing power quality issues. Digital instruments generally rely on discrete techniques requiring a measurement with window width of 12 cycles for 60 Hertz base power systems. So such long measurement window may not be effective to support decisions for equipment operating with faster dynamics, such as active power filters. So as an alternative for harmonic analysis, the deep neural network, DNN, can be used in the main processing stage to perform pattern recognition in power system applications. So this paper presents contributions to the perspective of harmonic estimation in applications related to electrical system. A deep neural network, DNN model to estimate harmonic amplitudes, and DNN model that require only a quarter of a fundamental cycle to estimate fundamental harmonic components. The Deep HarDec method is shown in this slide. The workflow shows that the input of the deep neural network, the Deep HarDec method, are a quarter of a wave cycle from a time domain signal. This wave cycle has 64 sampling points, which means that the sampling frequency is 15.36 kilohertz. And this data works as the input of our DNN model, which also has 64 neurons in the input layer. And the output layer has 4 neurons, one for each harmonic amplitude that we are interested in. And the data generation, the dataset is fully synthetic dataset. We built using Python 3.9 and with a nested loop. This loop sum the fundamental frequency, the fundamental sample with the other harmonic samples and amplitudes and phase shifts. And this nested loop iterates overall these features and generates more than 33 million samples with 64 sampling points in each sample. These samples pass through an normalization process and they are saved in the disk. The NN model was chosen from a grid search CV process that we are looking for the optimal model, the optimal DNN model. We are searching for the number of hidden layers, the number of neurons in each hidden layer, the function in that layer, and in the output layer. So after the grid search, we find out this architecture of DNN model, which has 4 hidden layers with 144 neurons in each layer, and ReLU activation function in each layer. And in the output layer, we have a linear function. So we trained our model for 40 epochs, as we can see in the figure. We also performed 2 case studies. The first one is with a mathematical model of a controlled rectifier, where it's possible to set the voltage, the grid voltage, the firing angle, alpha, and the load resistance and inductance. So we vary the load resistance and inductance, and we have this figure where we can see that the mean percentage error is less than 10% in all the cases. The second case study was performed with selective compensation, where we used a voltage source, an AC voltage source, as the power grid. The same mathematical model to the AC current as the emulating the non-linear load, and a current source to emulate and compensator, an harmonic compensator. So this current source receives the amplitudes from the DNN model as preferences, and inject the compensating current at the point of common coupling. This is the result of the selective compensation. We can see in the table that the individual harmonic distortion indexes are much better after compensation than before compensation. And the waveforms of the load current are worst. This waveform have more distortion than the source current. In terms of limitation, it's important to note that Deep HarDec may be computational more demanding. We can see in this table that Deep HarDec performs better in risk architectures, and fast Fourier transform performs better at CISC architectures. Deep, Deep HarDec demonstrates advantages, and it's important to analyze the trade-off between these techniques in order to choose the best one for each application. So the conclusion of this work is the suitability of a multi-layer perceptron (ANN) approach to estimate harmonic magnitudes from the 5th, 7th, 11th, and 13th orders. And the results show that an ANN model are recommended for harmonic estimation, especially for individual low-order frequencies. Moreover, using ANN model in the operational stage could facilitate the implementation of low-cost microprocessor in power converters. Thank you.
Thank you, Luis. Some questions? No? Could you just return to page 10? I think, yes. Could you elaborate why the compensation, the red line is not sinusoidal or like perfect like theoretically we expect?
This DNN only generates these orders. So this waveform in black has more harmonic orders. Yes. So we are only interested in compensate these specific harmonic orders. So this waveform in red has another harmonic orders that we are not interested in compensate.
Understood. That this is the most present, of course.
Yeah.
Okay. Thank you, Luis. Some other question? No? Oh, so thank you.